Hi friends, welcome to our channel. Let's look at a newly appeared problem, problem 4012, count of unfinished tasks after each shift. So I like this problem very much. So here, before we start, first let me specify the two key points in order to solve this problem in a clear fashion. The first is how to treat the carryover in the problem statement. The second is how to use binary search. So the first one is the crux of this problem, and also is where the complexity arises if you cannot treat it elegantly. So here we are given two integer arrays. One is called tasks, and the other is called shifts. So task I represents the time required to complete the ith task, and the shift j represents the amount of time available during the jth shift. So here the task must be processed in order from left to right. This is an important assumption. So first, if all tasks can be completed during a shift, then the shift ends immediately, and all the unused time in that shift is discarded, and then the next shift begins again from task 0. This is the one point. Another one is a carryover. So if a task is not completed during the shift, then processing continues from the same point, in other words, from the same index in that stack during the next shift, right? So here, a task is unfinished if it hasn't been fully complete. This includes a task that is currently in progress. So here we want to return an integer array called answer, where answer j is the number of unfinished tasks immediately after the jth shift. If you look at the first example, let's look at shift 0, which has time 9. So 9 is equal to the sum of the tasks, in other words, the total time. Therefore, in this shift, we can finish all the tasks. Therefore, so the remaining one is 0, right? Then we do the shift with time 1. Then we need to start over. So then it can finish the task at the index 0, that is 1. So the remaining are 2, right? And then when you do this last shift, that is 4, because the first one is already finished, you are starting from index 1, right? But there's no remaining time because 1 just used up. So you start from this 4, finish this one, but then you left 1. So that's why you have 0 to 1. So notice that in this third shift, you are actually starting from index 1. So if you look at example 2, so here, especially from shift 1 to shift 2, right? So here there's one remaining time, 1. You should add up to this 4. That's why in the last one you get 0, right? That's actually a crucial one. Notice also that both in example 1 and example 2, when we treat this one, or we treat from shift 1 to shift 2, especially this one, we're not starting from index 0, right? So if you treat like this way, it actually makes the coding not clean. So here there are some hints, so you can read through. So we build a prefix sum for tasks, where prefix I is the total time needed to complete tasks from 0 up to and include I. So the maintained amount of work already completed in the current pass through tasks, right? If adding the current shift length reaches or exceeds the total task time, all tasks are completed. So append 0 and then reset the completed work. So this is the one. Another one is that otherwise use binary search on the prefix sum to count how many tasks has been fully completed. If this count is C, then this is the remaining ones, right? So here in our solution, our main goal is to address this one. So we can set to always start from 0. Essentially the effect will be the same. Let me first write the code and then explain that point. First, we need to build a prefix sum. For the list. So here for tasks or shift. So here's let's say tasks. So we can use just to mix simplify. We change it to be A. So this can be very easy, right? So you can, for example, I can use this one. I just don't want to change in place for A, but you can do that. It does not matter. So for I in range, so from 1 to length A, so you can do pre-I. It's incremented by pre-I minus 1, right? So you can print out this pre to indicate that you are working with prefix sum. Let's run it. So for example, 144, you should get 159, right? So this is the one. If you don't want to write it like this, so another way is to use iter tools. So you can use say pre equals iter tools accumulate this A. This will give you the same set as above. But this is an iterable, so you can make it a list in order to demonstrate that. So you can print this again. You should get 159, right? So up to each index, so this is the total time needed. For example, if you want to finish the first two jobs, you need time at least 5. If you want to finish the 3 jobs, you need time at least 9, right? So this is the preparation step. So now let's look at the major code. So here we can initialize a result. So the result is going to be have the same length as each shift, as the shift. So for the unfinished task. So what we are going to do is we have so time or power. So let's see 0, and then so we can use n equals the length of this A, so number of tasks. So now we are going to iterate. So for A in shifts, right? So then the previous time, the current shift, so we are going to increment this by A. So this is the full power, right? So now what we are going to do is we're going to append. So how many tasks still left? So the total task is n, so minus the finished task. So finished task will be, I'm going to use bisect right. So it's going to change this one, p. So this is index. Let's see. So the insertion point. So you can do this. So what's this bisect right means? It means that for all index I less than this IP, so we have pre I is less than or equal to this insertion point, right? So this is exactly the meaning, right? So because in order to finish task, so for example, up to this one, so we need at least 5. So for 5, the insertion point should be 2, right? So the left side is less than or equal, right? If you use bisect left, it will be strictly less in here. So that's the thing. So you can compact this 2 line into 1, but here I split that. So here is minus IP. So now what we want to do is if P is greater than or equal to prefix -1. In other words, the total of the time in all these tasks. So we need to start over, right? So we set P equals 0. So then that's it. So we're going to return the result. Let me first test the solution, right? It passes the 3 cases. So now let me submit. So here, I guess that's the interesting part. We want to know. So let's like in example 1 and 2, why we do not start over. So here, why we do not start over is treated by this one. The key point 1. So how do we treat the start over or avoid start from avoid search from middle index, right? For example, if you want to write some low index like in as a starting point, that will be rather tedious because you need to retrieve the index as in example 1 or 2. But if you check the mechanism, you see that if it start from the index, then I still can pretend that it's starting from the beginning, right? So this is the very point that this takes carry over into consideration, right? This enables us to do binary search always starting from the beginning of the array, right? That's actually very important. Well, these two lines, this two line, so in particular, I'll see right here, if p is greater than or equal to -1, then we start over from the beginning. So this way, we no matter which shift, we always can treat the stuff as starting from the beginning. So this will make the code short and elegant. So I could say this is the key point. If you can digest this point, you digest the whole problem. Let me submit again to make sure it works. Yeah, with that said, I guess that's about it for the current video. Thank you for watching.